of solving log equations and inequalities, a recap of those concepts. This part 3 is where I discuss first when you need to condense or expand a log before you try and solve it. So if you see more than one log on a single side of an equation or an inequality, like in example 1 here, where I have 2 logs separated by a plus sign, and in example 2, I have 2 natural logs separated by a minus sign. I need to condense these before I try to solve them. So let's do that. I know that because I have a plus sign and or a minus sign. So I'm going to condense this first log, and I'm going to work this way if you guys don't mind. And I'm going to get a log base 3. Since this is a plus sign, I'm going to multiply these together. Log base 3 of the number 6x has to equal the exponent 3. Now I have a single log over here. This is a single log. This is a single log right here. So now I'm going to write it as an exponential. My of the number 6x has to equal my base, which is 3, raised to the third power. So 6x equals 27, x equals 27 over 6, and if I reduce that by 3, I get 9 over 2, or 4/2. All right. In example number 2, I have a minus sign. So this means that when I condense, I have to write the of the numbers as a ratio. So this becomes ln of 18 over 3x is less than 2. Remember that ln is the equivalent of log base e. So when I rewrite this expression as an exponential, I am in base e. Base e. All right? Okay. So I'm going to say my of the number 18 over 3x is less than e to the second power. I'm going to simplify, and I get 6 over x is less than e squared, and I'm going to get x all by itself, and I get x is bigger than 6 divided by e squared, which is 0.8. I'm running out of room there. Write a little bit smaller for you. I get 6 is less than x over x times e squared by multiplying both sides by x, and then x is greater than 6 divided by e squared, and I got to work this way. So x is greater than 0.8120. And if we write that in interval notation, it's going to be 0.8120 to infinity, or positive infinity. You might be asking, how come I don't need a lower limit? Well, I need to check it, and this says that x has to be greater than 0. And are my solutions greater than 0? They are, so I'm okay. It happened to flip signs, flip directions, the inequality flipped directions when we were actually solving, so that's why it looks a little bit different. We're going to do more condensing. Sometimes after you condense, you get a log on both sides. And if that's the case, then when you go to solve, you just set the numbers equal or unequal in the same manner that we've done before. So let's condense. I'm going to do this in a multi-step process. I'm going to bring this up and condense them all in one. Log base 6 of 0.1x squared has to be less than log base 6 of 10. And now my of the numbers have to be unequal in that same manner. So 0.1x squared has to be less than 10. X squared has to be less than 100. X has to be less than plus or minus 10, which when we write this is negative 10. X sits between those two values. So in interval notation, 5th and 7th hour, negative 10 and 10. All right? Now, can negative 10 work? Let's check that. It cannot. So we are going to have to stop here. I just noticed that. This, my lower limit is 0, right? LL, X has to be greater than 0. So there's no way that I'm going to be able to go all the way down to negative 10. So this should be a 0, and this should be a 0. All right, now ln, remember that's just natural log base e, natural log base e. So if I get down to a single log, I have to remember what base I'm in, but I'm going to condense first. And this looks complicated at first until you remember that whenever you divide by a number, particularly a fraction, it's the same as multiplying by its reciprocal. So that means 64 divided by 8/3 is the same as 64 times 3 over 8. And that's going to have to equal 4p. And that means that 24 equals 4p, and p is equal to 6. The kick on this one is that division by a fraction is the same as multiplying by its reciprocal. The reciprocal of 8/3 is 3/8. That's the reciprocal. One more thing I want to go over is that whole expanding issue. And we did this before we did common logs. And so all of these can be approximated with common logs, but I want to show you how the nuts and bolts work together so that we could use a table. Back in the day, that's all we had was a table. So notice that they give me, I'm going to use my highlighter here for a little bit, they give me the value of log base 2 of 5, and they give me a value of log base 2 of 7. All right, I have to use those and the properties to come up with a value for log base 2 of 125. Well, 125 is 5 cubed. So let's go back to our pen. My pen going here. And I can write this as log base 2 of 5 cubed, which is equal to 3 times log base 2 of 5, which equals 3 times 2.3219. 2.9, which is approximately equal to 6.9657. Sorry, that looks a little messy. Trying to be good. 70 can be expressed as a multiplication of 5 times 14, which is 2 times 7. So now I have log all of a sudden, there goes my pen again. Log base 2 of the number 5 plus log base 2 of the number 2 plus log base 2 of the number 7. Now we have a value for this. This is 2.3219, and this is 2.8074. But what is log base 2 of 2? Well, that comes out of our property that we really need to be able to recognize and utilize. That is plus 1. And when you add those all together, you get 6.1293. All right, the last one we're going to do is log base 2 of 49 over 5, and so I'm going to expand that by writing it as log base 2. 49 is 7 squared minus log base 2 of 5, and then this is 2 log base 2 of 7 minus log base 2 of 5. This is 2 times 2.8074 minus 2.3219, and we get roughly 3.2929. All right, thanks for listening. If you are still in class and you're watching this, try 10 and 18. If you get stuck, talk with a podmate, and I will video conference you tomorrow. Thanks.